Hello, welcome to the second lecture. Today we am going to discuss the initial conditions for the integration of the equations. Okay, yesterday or in the previous lecture we saw that in Maxwell electrodynamics, photons in the geometrical optic limit follow geodesics of the background metric. And we wrote the equations for those geodesics in Hamiltonian form, because this will be useful when we implement the integration of the equations in Mathematica, numerically. And once we have the equations, we discussed a little bit some conserved properties of the equations in spherically symmetric spacetimes and also in axially symmetric spacetimes without time dependence. Okay, so we had conservation of energy of the angular azimuthal angular momentum, and we also found the Carter constant, which allowed for the separability of the radial and angular equations for the Kerr-like geometries. So now we are going to analyze the initial conditions, okay, and how to relate the pixels of the detector with the conserved quantities of the differential equations. In particular, we want to relate the pixels of the detector with these constants of the motion, okay, of the angular LC, the azimuthal angular momentum, and Carter constant. Okay, so that's the plan for today. So this is important because when we have the detector, we are receiving photons, light rays that hit at different pixels, and these pixels produce the image that we observe. Okay, this is the observable part of the black hole shadow. But each pixel is hit by a geodesic, and this geodesic can be propagated backwards towards the black hole, okay, and the accretion disk. And therefore, what we want to do is to keep track of these geodesics. So, and each geodesic is characterized by an energy and these two constants, the azimuthal angular momentum and the Carter constant. So, if we were able to establish a correspondence between these labels of the geodesics and the pixels of the detector, then this will be very useful to map the to get the correspondence between the emission profile at the accretion disk and the observed intensity profile on the detector. Okay, so this is the plan. Now, when these geodesics are propagated from the detector to the accretion disk, they hit the accretion disk. Let me see if I can explain this. Let's wait. Yes. No problem. Let me just check. Yeah, basically this is the idea. So we have an accretion disk. It's very well represented here. And there is a photon coming from the accretion disk that reaches the detector. This detector in particular is located at a given observation angle. This is gamma. This is the observation angle. This other detector is at a different angle. This is on the equatorial axis. Okay. So when, for instance, this light ray is propagated towards the accretion disk, let's say that this photon is emitted from this point. Okay, from this point here. If we emit this the photon from that point, then that point is at a given distance from the black hole. Okay, and this the photon emitted at that point has an emission frequency. Okay, and the photon detected here has a different observation frequency because of gravitational redshift. Okay, so we need to know exactly where this geodesic that hits this pixel, where it has been emitted from. Okay, because in that way we will be able to compute the gravitational redshift. Also, we will need information about the disk, if the disk is rotating or not, and also about the specific intensity of the disk at that location. Okay, so there are many details we need to discuss. So, and this is part of the modeling of the disk. Okay, but aside from the modeling of the disk, the key thing is that we need to know the path followed by each geodesic and how this geodesic intersects with the equatorial plane, because we will assume that simple accretion disks that are flat and located at the equatorial plane. So basically, we will need to know when a given geodesic hits the equatorial plane. Okay, and depending on the radius at which this intersection happens, we will have a different gravitational redshift, and the motion of the gas of the depending on how we model the accretion disk, if the accretion disk is rotating, then we will also have a Doppler effect because of the motion of the gas at that specific location. Okay, so it is important to have control of the intersections of each geodesic with the equatorial plane. So this is the main point behind the construction of intensity profiles. Okay. But first, we need to establish this correspondence between the pixels on the detector and the labels, the conserved constants that characterize each geodesic. Okay, very good. So, as explained here, let me simply read. We will assume the detector is located very, very far away, so in the asymptotic Minkowskian region. This will simplify many things. This is not any absolute requirement. Actually, you can change this, but this complicates the physics. And since in observations, we are really very, very far away from black holes, we don't need to unnecessarily complicate the problem. Okay, so we will assume that we are really far away. For photons, we can set the energy to unity, but this is irrelevant because it's just a choice of units. And instead, we will write everything in terms of these ratios of the angular momentum z divided e and Carter constant divided e squared. So these are the relevant constants in the motion of photons. Okay. And now, let me consider the first example, the one that we saw here with the detector on the equatorial plane. Okay. So this is represented in this diagram here. Okay. And since the detector is very, very, very far away from the black hole, so any light ray emitted from the black hole that is able to reach this small detector plate, they will all be parallel to the equatorial plane. Okay, because if there is any angle, then when propagated backwards, since the black hole is so far away, it will not reach it. Okay, so we really need that light rays be parallel to the observation angle. Okay, in this case, the observation angle is pi halves. This is why all light rays go in that direction. And here I'm using Cartesian coordinates, and I'm aligning the axis in such a way that the light rays propagate in the y direction. Okay. Actually, the black hole is over here in that direction. Okay. And the black hole will have a similar axis. Let's do it like this. The axis, this will be the y, x, and z. Okay. But it's very, very far away. Okay. In that direction. And here we have the x prime, y prime, and z prime. Okay. So photons coming from the black hole will have a momentum, a spatial momentum, like this. Okay, it is pointing in the y direction. Okay, And since the conserved quantities that we have are related to angular momentum, what we need to do is to compute the angular momentum vector. So this is as simple as that, okay? So to compute the angular momentum, we just need to use the Newtonian definition of angular momentum. So we need the radius of the position vector and the momentum vector. The position vector of a photon that hits here, okay, is given by this. This R0 in the J direction, the Y direction, okay, is the distance to the black hole, no? From the center of the black hole to the center of the detector plate. And this R prime are the coordinates on the detector plane, okay? So they are represented here. R prime, we are centering the plane at Y prime equal to 0 here. And then we only need to care about the coordinates X prime and C prime. This X prime is parallel to the X on the black hole, at least very, yes. To simplify things, because we could, I mean, the detector plane should be orthogonal to the propagation of light rays. It needs not be orthogonal, but that's an unnecessary complication, okay? But it can be done, okay? So let's first consider the orthogonal orientation. And if you want later, you will see it's not so difficult to generalize the motion of the detector, in case you want to produce a video or something illustrating how black holes are observed. Okay, this can be done. So the point is this, that the angular momentum is given by this product, okay, and we just need to take this position vector. The momentum of the photon is simply P gamma is the energy times the direction, J, because we are moving in the Y direction. And then the cross product obviously is insensitive to the parallel component in the direction of the momentum. And the only relevant thing is the product of the components on the orthogonal plane times the J direction, okay? So I'm doing this calculation. We are using this R prime is represented here. We are using as coordinates on the detector alpha and beta. Okay, alpha represents the x direction and beta the vertical direction. Okay, so doing the scalar product, we get this thing. Okay, so in vectorial form, this is what we get. Okay, and this is the angular momentum. Obviously, this will be the Lx component, Ly component, and Lc component. Okay, so multiplying the vector L by the k direction, we get the L component, Lc component. And it gives simply the energy times alpha. So this is very interesting because now we have a direct correspondence between the location of the pixel on the detector plane, okay, and the azimuthal angular momentum, okay? So this means that if I choose a given alpha, I have the LC defined, okay? It could be the other way around, obviously, but for me, it's easier to play with the detector, okay? I don't know the angular momentum of the geodesics, but if a geodesic hits at a given alpha, now I know what is the value of its angular momentum divided E, okay? And now recalling the definition of the Carter constant, in the case of Schwarzschild, that was easier to remember, the Carter constant is basically the non-azimuthal part of the squared angular momentum, okay? So this means that we take the total angular momentum, we remove the projection in the z direction, and then do the math. Just take these quantities here. This L squared will be Lx squared plus 0 plus Lc squared, okay? And then Lx squared plus Lc minus Lc squared gives simply this quantity, okay? So now we see that the c-axis, okay, the coordinate beta is directly related to the Carter constant. Okay, and this is precisely what we wanted. Okay, now we have a clear correspondence between the two labels of each geodesic, LZ and Q, and the location of the pixels on the detector plane. Okay, so that's it. So this pair of constants is mapped into this or the other way around. Okay, so now we know the correspondence. We will start the integration numerically from the detector plane. Okay, so we will define an array of pixels on this plane. Okay, and for each pixel, we know exactly the alpha and beta we are referring to. And with this alpha and beta, by means of this correspondence, we know the values of Q and LC. Okay, and with those values, we can proceed to integrate the equations. We'll discuss a bit more about that a bit later. So this is the relation that we have obtained for when the detector is located on the equatorial plane. Okay. Now what happens if the detector is in a different plane, like this one, characterized by some observation angle gamma. Okay. So we are going to extend this analysis to the case of a different inclination. Okay. Here we are. And the situation is this simple. So I'm representing here this is the black hole reference frame in Cartesian coordinates. This is the detector plane, and as we see, we are choosing on the detector the Z prime axis aligned with it's along this gamma. Right? This is the inclination angle. So when gamma is 0, the axis coincides. Okay, it's that simple. C will be C prime. Okay, and in this way, we just need to do simple trigonometry or play with vector decomposition on a plane. Okay, so for the CXY axis, we have the vectors, we are just looking at the plane CY, okay, the CY plane. So we have the vectors K and J, okay? And when it is inclined, then the reference frame of the observer, of the detector, is inclined an angle gamma with respect to the original frame, and therefore we can express this K and this J in the basis of K prime and J prime. And that relation is here. This is simple trigonometry, okay? Look at the diagram and you will convince yourself that this is the right relation. It's just a rotation. It's very simple, okay? And once we have this rotation of the axis, we can invert it. Well, we can write it like this, and we can invert the relation. Okay, so that way we know the relation of these vectors on the detector plane with respect to the vectors on the emission plane. Okay, and now we do the same as before. We define the vector, the position vector of the photon when it gets, for instance, to this. If we have a photon reaching the detector here, maybe emitted from somewhere, from the center of the. Since the black hole is really far away, this center actually contains the accretion disk and many other things. Okay, so a light ray coming from that direction that hits this point has this form. Okay, and then the photon in this case is moving in the direction of K prime. Okay, because when they get to the detector, they are all parallel. Okay, remember that the detector is just a direction. Okay, it's like a star in the sky. So this doesn't have any size. It's just a direction. So all light rays are parallel to K prime. Okay, and this is why I'm representing the P of the photon as E times K prime. And then we do this scalar product. And this scalar product is very simple. Just remember, this is the example of the vector I multiplied cross vector product with K. It gives minus J prime, and that's it. So the angular momentum takes this form, okay? And then we project, and when we project this L gamma written in this basis with the K, because this is the LC is defined in this way, with the K of the black hole frame, okay? Then the scalar product between K and J prime follows directly from this. K times J prime gives minus sinus, this quantity, okay? It's basically, yes, is that. That's J prime is cosinus J minus sinus K, so the product K J prime is minus sinus, okay? And this is what we get here. So when there is an inclination angle, this is the relation between the pixel and the angular momentum, including the angle, okay? When the angle is pi halves, like the equatorial plane, we get the result that we saw here, okay? That was simply this relation. Now we have the inclination angle contained here, okay? This will be important because the geodesics are not the same. Depending on the inclination, we will see different things on the detector, okay? So this is the correspondence between our alpha and the azimuthal angular momentum. And for the beta, we can do the same. Remember that we need the non-azimuthal angular momentum. So we need the components Lx and Ly. We squared both, add them. And for Schwarzschild, we will have Q given by this. Okay, this is quantity. And then we just see that beta is related to a Q and the inclination angle, okay, in this way, okay? Before, when we were on the equatorial plane, we only had this, we didn't have the cosinus contribution, okay? This one. Now we do have an effect due to the inclination, okay? So that's it. So basically, this is what we have learned. That we have to define a grid on the detector. Actually, this is what really happens because our detector is a CCD. Well, if we are looking at optical images, we would have a CCD chip, okay? And this is basically an array, rectangular array of sensors. And we could define a rectangular array of alpha and beta, which are our pixels. And then for each alpha and beta, for a given inclination angle, we determine the corresponding azimuthal angular momentum and the corresponding Carter constant, okay? This has been derived for Schwarzschild because it's easier, but for the rotating case, it's essentially the same thing, simply adding a contribution due to the orbital motion of the rotation of the black hole. And this is the relation, if you remember, in the case of rotating black holes, we have this relation, and then the correspondence between beta and the parameter, the constant Q, is given by this. So basically, we are adding this A, and A was the parameter that controls the angular momentum of the angular the rotation, the angular velocity of the black hole. Okay, very good. So that's it. For every pixel on the detector, alpha and beta, we know the value of LC and Q. And with LC, we have the initial condition for the azimuthal momentum, okay? With Q, we get the initial condition for this other momentum, because there is this relation, okay, which translates into this. And then we need an initial condition for the radial component of the momentum, okay? And this comes from solving the Hamiltonian constraint, okay? Just let me show you. This is here. This is a summary of what we have, okay? So we had Hamilton's equations for the geodesics, okay? So this means that we have 3 equations for the position coordinates, 3 equations for the momentum coordinates, okay? And we need to integrate each geodesic, we need initial conditions for these equations, okay? So for the position variables, for these position variables, what do we need? Well, since the detector is very far away in a given direction, okay, the direction is fixed for all the photons. The photons are moving in that direction, okay? Basically, because the detector from the black hole to the detector, there is no angular size, okay? So this is why they are all going in the same direction. And that direction is, by definition, that the azimuthal angle is 0, could be anything, okay, but just an angle, some constant. And the angle and the polar angle is the inclination of observation, okay? These are fixed. And the distance from the black hole, from the center of the black hole to the center of the detector, okay? So these quantities, these initial conditions for the position variables are the same for all photons, okay? We don't need to worry, just the detector is there. So that's the position of the direction and distance of the detector. So that is fixed for all photons. Now, what changes from photon to photon are the initial conditions for the momentum, okay? For the azimuthal momentum, we have this conserved quantity, LC. And this LC, as we are explaining, is determined by the alpha position, okay? By the value of alpha, by that pixel, the position of that pixel, and the inclination angle, okay? So once we have the inclination angle and decide which geodesic, which pixel we want to study, we know the corresponding LC. And with this LC, we have the initial condition for that variable. The same happens with the polar momentum, okay? It is just given by the constant Q and these other quantities, okay? But this is a property of the black hole, it's a constant. This alpha is information that comes from the pixel. Q comes from the pixel as well, and this is the inclination angle. Okay, so these 2 momenta are now defined from the choice of the pixel. Okay, and the only remaining component that we need to integrate the equations is the initial radial momentum of the photon. Okay, and this is the most algebraically complicated part, but it's trivial, because from the Hamiltonian constraint, for photons, the Hamiltonian is 0. So we just need to sum all these quantities, that is written explicitly here for rotating metrics, okay? And then what we need to do is, since all this is 0, we just isolate this guy, we put it here. The GRR comes to the other side, dividing, and then we put all these things. And we already know the value of this one, the form of the metric. So this is what determines the radial momentum. A detail is that the photon is now propagated backwards. Okay, even though the photon hits the detector moving forward, it would have a positive PR. Since we are integrating backwards, we need to put this minus sign in front of the square root. Note that this is a square. Okay, so we need to take the square root and we choose the minus sign. Okay, and these are the initial conditions that we need to integrate our equations. Okay, very good. So we have Hamiltonian equations, we have initial conditions for these equations, and these initial conditions are related to the position of the pixels on the detector, which is really great. Okay, so now we have a clear correspondence between our measuring device and the the photons that are going to reach the black hole. Okay, very good. Now let me explain a little bit what we expect to see. Okay, so this is a representation of geodesics in Schwarzschild. Okay, the Schwarzschild, this is the black hole. This guy in the middle is a black hole. It's evident. Okay, this red thing that we are representing here is actually should be infinite. This represents the accretion disk. Okay, the accretion disk. And actually, the accretion disk could be extended everywhere. Even it could even fall into the black hole. Okay, but I decided to represent the accretion disk only between 6, okay, upwards, because as you probably know, in Schwarzschild we only when circular orbits, stable circular orbits, only exist from r equal to 6 upwards, no? For values of r larger or equal to 6. And this 6 is called the ISCO. ISCO. And the ISCO is the innermost stable circular orbit. Okay, so if we consider an accretion disk that is stable, stationary in time, you know, it's been in equilibrium and blah, 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 and is not falling into the black hole, then that accretion disk would be defined from R ISCO to infinity. And obviously the distribution of matter and it needs not be homogeneous over the disk. There will be some higher density closer to the black hole where gravity is more intense. Okay, so we could perhaps represent here the intensity profile, saying that the intensity is maximum here and then decays. Okay, so in that sense, that the emission of electromagnetic waves from the region near the ISCO is more intense. Okay, this is what I'm representing here. So this is how we are looking at the ISCO. So this is a section, a cross section of the accretion disk and the black hole, and the observer would be very far away in that direction. Okay, so this geodesics, this green geodesic, for instance, comes from very far away in that direction. Okay, so actually I'm propagating it backwards. This is part of my numerical integration. Okay, so that light ray is propagating like this. Okay, and since the impact parameter of this geodesic is relatively high, is around 10. The impact parameter I'm referring to this quantity. Okay, it is 10. Then this green light ray is weakly deflected. So it is deflected, but not too much. Okay, so and it will move to infinity in that direction with a slight deflection. Okay, so note that this geodesic intersects the accretion disk at this point. Okay, let me use a different color because this is becoming dirty. Which one? Blue. Okay, let's say that the geodesic hits the accretion disk at that point, and what that means is that a photon emitted from this point may follow this geodesic, this path. Okay, and then will reach the detector very far away at infinity, basically, where the detector is. Okay, so the different colors are representing the different types of geodesics. Okay, so these green geodesics that are in this interval up to this region, as you can see, they are deflected by the gravitational field and intersect the black hole only, the accretion disk only once. okay? So these green geodesics represent the direct emission, what we call the direct emission of the disk. So there is only one intersection of the geodesic with the disk, because as we can see in this one, it is deflected and continues traveling to infinity, okay? The same happens to all these green geodesics, okay? And this one, this is close to the boundary because this one is asymptotically moving parallel to the accretion disk, okay? So since they are parallel, they will not touch at any point. So this means that this last green geodesic is essentially the last one to intersect the disk only once, okay? Good. Because then we have the other part, the orange geodesics. This orange interval, these intervals are determined numerically, okay? These orange geodesics, as you can see, the first one is very close to the green one. This hits the accretion disk, or at least the equatorial plane, okay? So this is the equatorial plane. Equatorial plane. It hits the equatorial plane once, okay? But at infinity, it could hit again the equatorial plane, okay? So since we don't know how big or how far the accretion disk extends, okay? So we could say that this orange geodesic cuts or intersects the axis, the equatorial plane, at least twice, or well, actually only twice, 2 times, okay? One here and one very far away. And this other one, the geodesic that is closer in the orange sector, that is closer here, as we can see, it intersects the equatorial plane twice, okay? This is then propagating in that direction, okay? And there is another that is here that then will be parallel to the equatorial plane again. Okay, you can see this ones. Okay, so this is again the limiting geodesic in the orange range that characterizes those geodesics that intersect the equatorial plane twice. Okay, so this means that a photon emitted at this point can reach the detector. Okay, it's moving in that direction and we'll get to our detector. Okay, but it means also, and this is part of direct emission because there is only, this is the first intersection. Okay, this is like this one. All these geodesics are direct emission. Okay, the photon is emitted and gets to the detector. This other photon, okay, if it is emitted in this direction, obviously it will not reach the detector. It is lost in space, okay? But if it is emitted downwards in that direction, right, then the strong gravity is acting in such a way that this photon is strongly deflected and then comes here and joins this first photon. So this geodesic will contribute to the detector, to the pixel with 2 photons, okay? One that is emitted from here and another that is emitted here. And obviously the distance in this case, to this photon, from this emission point to the center is in general different from that distance, okay? That means that in particular, that the gravitational redshift experienced by this second photon is different from the gravitational redshift experienced by this other photon, okay? So when we compute or add the intensities of these 2 photons on the detector plate, we need to take into account this fact that they intersect the equatorial plane in different locations, and therefore they contribute with different intensities because the redshift that applies to each photon is different, okay? So This means that when we proceed with the numerical integration of the geodesics backwards, we need to extract information about the intersection points of the photons with the equatorial plane, because in the equatorial plane is where the accretion disk will be located, okay? In some points, we may not have accretion disk. That depends on the model of accretion disk that we use, okay? But this is a freedom that we have. We have different kinds of accretion disks. One example was this one that is defined from the ISCO outwards, okay? But there are other accretion disks that represent matter that is really falling into the black hole, okay? So in those cases, the accretion disk is defined really everywhere, okay? It's defined even in this region. Yeah, this color is not really very fortunate. So it's even here, okay? So this is why it is important to determine for each geodesic the intersection points with the equatorial plane, with independence of the accretion disk model considered, okay? Because the intersection points are a property of the geodesic, okay? It's a property of the spacetime. The intensity profile is a property of the disk of the astrophysics, okay? So these are two different things, okay? And we need to combine the two to generate the intensity profile of a specific disks, okay? A given disk generates an image, a profile, and another disk may generate a completely different image, okay? Being the geometry being the same, okay? Very good. So what else? Yeah, so we discussed the green, the orange, and now we have to discuss also these red ones. These red ones. These red ones are intersecting the disk, for instance, here, the equatorial plane here. If we trace them back, they are intersected here, and they are somewhere here. So this is a small region that is very important because this is the innermost light ray of the red band of this red group. Okay, this one is virtually orbiting in a circular orbit. So it is turning around the black hole many times. Okay, but that doesn't really happen. Okay, so usually photons can orbit like let's say, okay, it comes once, hits once, two, three here, and then it moves away. But we can increase the resolution in this region and find photons that intersect the accretion disk 2, 3, 4, 5, 6, 7, n times. Okay, but the number of geodesics in that region is extremely limited. Okay, there are very few. Okay, so but those geodesics are very important because those define the photosphere. This yellow thing, this continuous line is representing the photosphere, and that's the limiting surface that separates the photons that escape from those that are captured by the black hole. Okay, so everything in this region is captured by the black hole, and everything above that, above the red, including the red one, they are free to move. Okay. So, so this is the classification of the geodesics. Typically, we speak about the direct emission, which are those that cut only once the equatorial plane. The lensed emission that represents two intersections. Okay, it is lensed because it is strongly bent, but not too much. Okay, only two intersections. So the light emitted to the south south is here, okay? We are in the North Pole. So this light emitted from here can be strongly lensed and reach the detector, okay? Very good. That is the length emission. And then the photon sphere is made out of those photons that have 3 or more intersections with the accretion disk. Okay. And I was discussing the gravitational redshift, okay, because it depends on the radial position of the photon when it hits the equatorial plane. But we can make the accretion disk more realistic, and instead of assuming that those particles are static, we can add some movement to those particles on the accretion disk. So if the accretion disk is rotating, so those particles that emit the photons have an initial velocity, and that velocity induces a Doppler effect, Doppler redshift or blue shift. Okay, so to compute the effect of that Doppler effect, we need to know the velocity vector of the emitting particle. That this is something that we model. Okay, we say that this fluid that is making up the accretion disk is moving with this velocity profile. This is something that we give. Okay. And it can be a Keplerian motion, for instance. Okay, in orbits around, if we are in the beyond ISCO region, we know that they are making circular orbits. Okay, so that's perfectly well defined. But to compute the Doppler effect, we need the scalar product between the velocity vector of the emitting particle and the form momentum of the photon. Okay. And this means that besides knowing the position at which the photon hits the equatorial plane, we also need to store or to save in our array of data the free momentum of the photon, because that information will be crucial to compute the Doppler effect. Okay, otherwise we lose that information. Okay, so if we want to make our model relatively realistic within all the limitations that we are imposing, all the simplifications that we are imposing, at least the computation of the Doppler effect is something that we have to do. So this is something that this is the second element that is important in our integration. So given the equations of motion, we give the initial conditions at the pixels of the detector. We integrate backwards and identify where the geodesics hit the equatorial plane. Okay, the equatorial plane is simply the condition cosinus of theta equal to 0. So when the geodesic satisfies this condition, well, we stop the integration and save data. Okay, and the data that we save are the radial location, okay, and the free momentum of the photon. That is PR, P theta, and P phi. But P phi is conserved. Okay, this P phi is always the same, so it's LC. So we only need to compute these two. Okay, very good. And that's something that our code will have to do. Okay, very good. So good. Now, now that we know how to integrate the equations and what information we are looking for, we need to understand the relation between the emitted intensity profile and the detected intensity profile. Okay, so let me skip this for a moment and go to the simplified models of emission. Okay, these are the emission profiles. Some examples. So these are simply representations of this function. Okay, this function is a fit. It's a function that fits well or relatively well some time averaged models, realistic models of general relativistic magnetohydrodynamic simulations. So this means you take a bunch of very intelligent astrophysicists able to do super complicated numerical integration with general relativity equations, fluids, magnetic fields, turbulence, and all that, okay? And they model an accretion disk, okay? And they have the time evolution of that accretion disk. Then they consider a time average, okay? Because the measurements of the accretion disk take some time. So the instantaneous intensity distribution is not important. What you need is an average over time. So when you compute the time average, you get some spatial distribution of intensity, and then you just use these functions to fit those intensity profiles. And it turns out that this function fits relatively well some realistic accretion disks. Okay? Realistic in the sense of having all the physics inside, okay, all the complicated physics. So we are simplifying, and we buy these functions. So these functions are simple. They depend only on a few parameters that are this parameter mu that tells us where is the maximum of the emission peak. In particular, for instance, here we have a maximum. Here we have another maximum. These are different maxima. Okay, so these have different values of mu. The width of the peak, this has a width. Okay, and this is very different. Okay, you can see two different emission profiles, right? Very different. These two are located around the ISCO, okay? And these others, they are all falling, all these are falling below the event horizon, okay? This should be the photon ring, the photon sphere, PS, okay? So you can see some intensity profiles produce intensity, non-zero intensity in different regions. Right? This is the maximum, okay? Maximum, then it decays very quickly. Okay, so, and they have been normalized to the maximum intensity. It's important to note that in these intensity profiles, the maximum emission is, for instance, in this one, the maximum emission is at this point, but this point is near the event horizon. So this means that the gravitational redshift in that region will be very high, okay? So even if this point is the one with the highest intensity of this model, the observed intensity may not be as big, as significant, okay? And maybe a more distant point where the gravitational redshift is sufficiently small appears brighter than this one, okay? So you need to start thinking in that way, okay? Good. So now that we have a given intensity profile, that is what I was representing here when I did this curve. For instance, we put the maximum intensity profile here, and then it decays exponentially, okay? Something like this, okay? This is the maximum intensity in different locations. Okay, now that we have that, we know that when a photon hits here, we'll peak some intensity and we'll transfer that intensity following that geodesic towards the detector, okay? Very good. So this is once we have all the geodesics and the intersection points of each geodesic with the equatorial plane, once we specify the intensity profile, we will be able to transfer this specific intensity at the emission point to the detector, okay? Taking into account the gravitational redshift that depends on the radius and the Doppler redshift that depends on the position and the momentum of the photon, okay? So this is why different models, intensity profiles will produce completely different images, okay? And then we have the inclination angle that adds additional effects, okay? But in order to transfer the intensity at the emission, from the intensity from the emission points to the detector, we need to understand how energy is transported in this space-time and with this electromagnetic theory, okay? So that means that we need to go back to the electromagnetic field equations, study the transport equation, and see how that transport equation behaves, okay? In our case, in Maxwell, we can we can do the following. At each point, this is illustrated here, no? At each point on the accretion disk, okay, particles are emitting photons, electromagnetic radiation in all directions, okay? Very good. So the density distribution of photons, the density distribution of photons depends on the specific point where you are, because different points will have different intensities. This is illustrated here. So the maximum intensity is near the ISCO, and then it decays, okay? And the distribution of photons depends on the position, but also on the momentum of the photons, okay? Because maybe at this point, the physical mechanisms that are acting in the generation of photons only produce photons up to some frequency. They are unable to produce photons beyond a certain frequency. So that means, or in some directions, for some reason, there is a restriction that some photons cannot be emitted in some direction, okay? So the density distribution of photons is the function that determines how photons are emitted at each point and in the different frequencies, okay? So, and in Maxwell theory, if we assume that photons are not absorbed, they don't have interactions, and blah, 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 then this density distribution should be conserved along geodesics, okay? So if you need a simplification, if you really need a simplification in this process, this is the one, okay? Because if you begin to add here interactions, then you are completely dead, you are lost. Well, no, you are not lost because we are paid for that. We would spend a lot of time integrating these equations in different ways. But since this is a simplified model, we simply will assume that the density distribution of photons is conserved along the geodesics, and then this has some implications. In particular, from the density distribution, from sigma, we can define the photon number, the photon number in phase space that is given by this. And then what we want to do is to relate this photon number with the photon density and observable quantities, okay? And the observable quantity is the specific brightness. Brightness is something that we can see with a telescope or radio telescope, okay? This is a measurable quantity. These are theoretical quantities. So what we do is we relate this intensity, the specific brightness, which is the energy per unit area, time, and solid angle and frequency. We use it to define the energy transported by photons, okay? And then we interpret this energy transmitted in this unit of area, unit of time, and solid angle and frequencies as per frequency. If we have, if a photon has energy h, Planck h, nu, then the total energy transported by that density of photons is simply the density of photons times the energy of each photon. Okay, this is the energy transported. Okay, and then we can compare this with the, well, this dn is written in terms of sigma, and once we need to expand this volume element in space. This is a volume element, and remember, we have a transverse area and then the motion of the photon. The other length is c dt, okay? And then the volume in momentum space is just p squared dp, but this p per photons is written as h nu, the frequency, see? So we can replace the momentum p by frequencies, and then we have in the end this nu cube here, this differential of nu, blah, blah, blah. And we find that this sigma is related to the specific brightness by means of this relation, okay? And now, I'm concluding. Since this quantity is conserved, okay, then we have that the intensity at the emission point, the intensity at the emission divided nu cube, the frequency at the emission, is related to the observed intensity divided by the cube of the observed intensity. Okay, these quantities are conserved, and this is what allows us to determine the observed intensity in terms of the emission profile. The emission profile. And then we have this ratio between frequencies, the emission frequency and the observed frequency. So this is the intensity profile represented by this function. This is the emission. We are modeling the disk, the emission profile, okay? And then once we inject or define the emission profile and know the relation between frequencies, the emission and observed frequencies, we can compute the intensity observed at the detector, okay? And that's it. Now the relation between the emission and observed frequencies are given by the redshift, no? The redshift factor that is represented by this quantity. And as I said, we need the velocity vector of the fluid that emits emitting photons. And this P mu is the momentum of the photon. And this momentum of the photon is represented by the energy, the PR, P theta, and P phi that we obtain from the numerical integration of the geodesic equation. Okay, so this factor G is computed numerically. Okay, so once we determine the intersection points, we can compute these things. And if we model, for instance, in a Kerr metric, and we assume a disk element rotating with some angular velocity, so the fluid will have this velocity vector, and we can compute the redshift factor explicitly in this manner. Okay, so we will have to put this in our numerical code to transfer the theoretical emission profile to our detector through the specific geodesics of that spacetime. Okay, and this is the theory summarized at the speed of light. And next day we will see how we can implement all this in Mathematica, in a numerical, in a code that integrates the equations, stores the information about the intersection points and the momenta, and then makes the convolution of that information with specific intensity profiles located at some observation angle. Okay, and we will see finally the intensity profiles that different theoretical emission profiles produce in our detectors. Okay, and that's all. Thank you for your attention, and we'll see you in the next lecture. Bye-bye.